Okay, now, yeah. Thank you all for being here. Thank you for the invitation. It's a pleasure to be here. And so I will keep talking about the speciation, and thank you, Marcus, for the introduction. And it's a huge responsibility to talk just after Marcus. But okay, let's move on. So as Marcus mentioned, we have a huge diversity, and to understand what are the mechanisms behind this is still a debate. So it's not completely understood what the mechanisms behind this huge diversity. And as Marco mentioned, we have this allopathic speciation when you impose a barrier here and you divide the population. And just in a neutral event without selection, we can end up with 2 species just because mutation that occur here cannot move to this population. And to understand how sympatric speciation could emerge is still a debate, and if it could emerge in neutral, as Marcus just mentioned, I do not need to go in detail here, we just have a talk about that. And my question that I want to talk to you today is coming from this scenario when we have allopathically, for instance, 2 islands, and we impose migration between these 2 islands, and then we end up, if this migration is huge enough, you end up with a sympatric in the same spot. It's not the sympatric in the same way that Marcus just mentioned, because here they will be exactly in the same squared. We have just 2 squares in his model here, just 2 islands. And our proposal is to understand how migration plays in this scenario, because in nature, having a real allopathic is a barrier that avoid the migration here. It's not so often, so maybe migration plays something here. And so in this talk, I will go through those manuscripts where we have done, and Marcos is one of our collaborators, and also Paulo Campos from University of Pernambuco, and some student now, Flávia is also a professor at Unicamp, Salete is a postdoc at Universidade Federal do Paraná, where I'm from. And for sure, many people are here, and just to thank them. And we'll go through those, and then I will end up with what we are doing now. So the basic idea, as just introduced, we can model individuals here. I just put -1 and +1 instead of 1 and 0. So it's the same idea as we learn. And when we have a pool of individual in a given spot, each dot here means 1 individual. And when these 2 individuals mate, we have an offspring that is a recombination of the parents, and the offspring can have 50% of inherit the locus of individual 1 or the gene of individual 1 or 2, and plus a mutation, that is a mutation per locus. So here's the genome size B, as we just saw. And the idea of a neutral model is like for each one of 2 individuals, we let them mate, have an offspring, and die. So how the model will work, we pick just 2 individuals, pick 1 individual to be the mother, and this mother will look for the father. We'll let it look for n fathers, and n is the population size. And if find a father, then we can have an offspring, and the offspring replace the population. So the individuals who mate then die, and then this cycle repeat. So the model is a simple model, neutral model. There is no selection towards a given phenotype. And then next question will be, how many species can arise from this model? And to define a species, we need to impose what will be a species. And And if you impose a mating restriction, as Marcus mentioned, we can define species as the group of individuals that allow gene flow. So given this restriction for mating, for example, here, each arrow here means these individuals can mate with this because they have the similarity enough to mate. But at this guy here, for example, do not mate with this, although the colors are still blue here, sorry. But a mutation that comes here can grow through here by this line here, for example. So we call this one species. So as the time goes, we can build the link of possible matings, that is the genetic, based on this similarity, the genetic similarity. We can build this network. And so here would be one species. Here would be another species, just one species here, just because there is possibility of gene flow. And we can end up and see how many species emerge in this island. So we can also go to infinity genome, and we can write the master equation. So what is the probability of having a gene plus 1 at time t plus dt? So it's the probability of already having this genome, so for each locus here. So times the probability of not mutation, no mutation here, plus the probability of a given locus minus 1 having a mutation and being plus 1. With that, we can, so with this master equation, we can integrate this, and we have how the probability of each locus would evolve over time, and we can calculate the expected time and how this similarity would evolve among two individuals. So just an approximation how we could do this for infinite genome. I will not go more in detail on that, but just saying that we could model just looking for this similarity and build our network based on this similarity. If two individuals, alpha and beta, are more different to this minimum value, then I will say they cannot reproduce. And then we can build the network of similarity and define species in the same way that I just explained. So what we have done with this, now let's consider this model in the one spot. So let's consider two spots, just two islands, and let allow migration from individuals from one island to the other island. So each individual here will have a probability epsilon to move to the other island. And this problem is completely symmetrical. We considered islands of the same size, which means same population size. So symmetrical problem. So the basic parameters of the model are the minimal genetic similarity to define, that will help us to define species, the constant population size, what is that, and the migration. The migration is also constant here. And so I will show you how it will work here. For example, each dot means one individual in one of these islands. And what we expect from allopatry is that if you let the migration 0, here is a graph over time in island 1 and island 2, and the colors, same colors, means same species. So they are in different islands, but the genetic similarity is still enough to link. If they met, they would have they could have an offspring. But as the time goes on, here we see that the colors change, which means that we have an speciation event. So it's actually, maybe it should be two new colors just because they are being different. So, but to save colors, I decide just to highlight here that I have one speciation event. So for one island, I keep the same color, and the other just change the color. And So here is just an example of it works. Now we let the migration 0.4% probability of each individual move. And when we see this over time here, we can see now speciation start to emerge. And we have these small groups here, small groups there. And what you see here, a kind of pattern that for a long time we thought there was an error in our program, is that usually we have one island with one big species, and the other island we have many species. So this is, wow, what is going on? So this is not a error. I made the code, and then Marcus made his own code, and another person made this own code, and all codes do the same thing. So, and then we spend the time trying to understand how this asymmetry could emerge. And so, well, I think let me see here. Let me try to explain by here. And the basic idea is that this asymmetry just emerged, so the problem is symmetrical, but it's emerged, and once it's emerged by random, it stays stable in the sense that, for example, here we have this big species. If two individuals migrate from here to here, they can found a new species. So they move to the other island, and they cannot cope with other individuals, which means that a potential of new species can emerge. But the other way around, here, once you have 3, 5, 6 species, the chance of 2 individuals of the same species migrate from here to here is even lower, because now we have more diversity in this island. So this kind of asymmetry is an emergent pattern that emerged in this model. So here an example how our conclusions, how our results change with different genome size and with different migration. So here the example that I just showed you, just turn the island around. Time now is here, island 1 and island 2. This line here means that they are the same species, and from this time on, we have 2 species. Migration is turned off, so that's why. But here, all this line is migration turns off, but as we increase the genome size, we increase the possibility of combination, possibility of number of species, and we start to have sympatric speciation. But we don't have that allopatry clear here because we have a speciation occurring here. So, but the results that I think more interesting are these 2 examples here. And here it's clear that asymmetry, you have just big pink species, and the other island with many species here. And if we keep increasing the migration, we end up, if the migration is big enough, we end up with just 1 species. And I think it's really nice because it's talk to ecology. So if you go to the textbook and study how evolution emerged, how diversity emerged, they used to say, if you have a barrier, we have 2 species. But if they migrate, you will end up with just 1 species. But what we are bringing here in this manuscript, that is not like that. Yes, we have those limits that it's well known, but we also have this situation where when migration is really slow, you can increase the diversity more than just 2. You can increase this for many more species. So we can have this situation when migration can favor speciation, and this favor we already knew from the textbook. So here, just to summarize the results, here's the total number of species as migration increase. Here's the low migration as function of genome. Here is that case where the genome is infinity. Here's an approximation that we did mainly, Deborah and Marcus, with analytical results, trying to understand what was going on here. And, but, and here also not just with genome equal to 1,000, but just 2,000, we have this peak here, is the thing that is more interesting here. And also another way to see this is how that asymmetrical pattern was common, how this asymmetrical pattern is related to this speciation here. And we saw that, in fact, this asymmetry here is just the difference between the number of species from one island related to the other island, and how they differ, and we have this as guiding of this speciation. It's not, we could say, oh, but this random, it's just random, we test this, we test the distribution, what would expect if it is just an asymmetrical, just by random, or if it is just by random, and so just by random, sorry, is the red one, and the blue one, sorry, here is a blue one, this plateau here. It is the situation that we have from the model. Here's the histogram for the different number of population, this number of species, the richness, yeah, the number of species from one island minus the other island. So what we have from our simulation at this plateau here, we have more often asymmetry than expected by random. And with that, we go again to our videos to understand what was going on. And we saw basically these two modes of speciation. And one is by founding population, as I mentioned, just when a small population migrate to the other island, and as the time goes on, it ends up as being a new species. But we also saw some speciation that individuals from this island migrate to the other island, and they can mate in the other island, but they bring too many novelties, too many mutations in their genomes, that it allows sympatric speciation. So here we call sympatric speciation induced by migration, because if you turn off the migration, those kind of things does not occur. And our next question, okay, but migration is not always, let me just check. Or maybe your cell phone is here. Okay, I think we have a little bit more time, right? So our next question, was, okay, but migration is not constant in nature. It oscillates. So if we think these two islands and we take the sea level oscillation, we took the real sea level oscillation from 800,000 millions. And with this data, we say, okay, when the sea level goes down, we have these two islands that can communicate, and then migration is on. And when the sea level is up, these two islands become isolated, and the migration is off. And for sure, we need to decide what would be this threshold. What is this threshold to migration on and off? And we stood different threshold, which means different sea level. I just forgot the terminology. The seabed deep here. Yeah. And so it was a comment in a manuscript that we did the same. And here, just to remember, this is not a low migration. It's already, it's 4%, not 0.4%, which means that with this migration, if the islands are connected during the whole simulation, we end up without speciation. And here, just increasing the migration 10 times. But when we impose this on and off, and here, if you consider the seabed really high here, so it's the isolation, here the black lines means the isolation events. And this just short events of isolation is enough to increase the number of species. But for sure, if this migration is still huge enough during this, the other time, that we can end up without speciation. And we keep doing this with different sea level dip, and we see this oscillation of migration promoting speciation. Not just that, but when we isolate a lot, that is the basic idea, how speciation emerge, we end up with few species then in this scenario, for example. And again, we see the migration events promoting speciation. So here is basically the same, just here these oscillations are not regular, so to understand better, we test with a regular periodic oscillations here, and we test the period, we test this time lag on and off, and here we just measure the number of species by the end of the simulation. And basically what we saw here is here let's see under high migration, as these dots here, the peaks or means so the peaks here means the simulation that end up with a higher number of species as the situation where the island end up isolated. So if the migration is high, we need isolation for speciation, is basically that. But if the migration between the islands are low, we end up with high species when the end of the simulation, for example, here, you end up the simulation with the islands communicating. And we also look at the phylogeny, and thank you, Marcus, for explaining this phylogeny thing. And we look for the same problem, how as the phylogeny, when we saw many, so here means extinction events. And we see many extinction events, and this simulation here, we also had some species just last few generations. And here, many extinction events. And we compare here the phylogeny of the completely phylogeny when we have the speciation with the phylogeny when you exclude the extinction. And our idea is that if you go to the real data, you usually just have that one. We usually don't have fossil records. They are so few. We lost the information about the extinction. And our question is that, can we infer about the process that is going on in the island, looking just at those phylogeny? Could they say, looking for a phylogeny, say, maybe is that migration is playing an important role here? So what we saw, just to summarize, that the balance of the phylogeny seems to be a sign of the speciation mode. When we have that asymmetrical thing, oh, just finished? Okay. When we have that asymmetrical thing, seems to let our phylogeny more unbalanced. So I should finish, I would say now what we are doing now, we are considering multiple islands, and with Saletti as a collaborator there that got interested in this model. And we are doing now with archipelago with many islands and see that still this migration can promote things. So I will, maybe it's better to move on and just say thank you for everybody that are somehow involved in this project.
Thank you very much, Sabrina. This is a very beautiful mechanism. So we have time for questions now.
Thank you, very interesting. Just a question I didn't understand about the pulsating migrations. When you have a periodic pulsating whatever, migration rate, shouldn't it be related somehow to the generation time, so you have some entrenchment between the speciation and the migration frequency?
Yeah, maybe maybe in a short time scale should be that. I don't know if it's what you think, that they usually migrate and in a mating season, something like that we're thinking. No.
I'm thinking that if the migration frequency should be somehow related to the generation time.
Yeah, so each time here is a generation time. So each time step here, we have one loop of the generation. So how many generations, and yes, actually, how many generations they need to be isolated to have one new species is one process. So if you so here once, in this case maybe not, but here, here when we need the barrier to have a speciation, so they are isolated here, and then we end up with two species. So how long we need to let the semen without the migration to have this? So the time that lasts for a speciation, the shorter time for having speciation would be the better time to increase the speciations. Is somehow what and the answer is it's yes. And because we also have the problem, if you let the system a long time isolate, you end up with, as expected by the neutral theory, that we just isolate two populations. They are equivalent. You end up with just one species, just by random, one will end up with so just isolation is not the better mechanism for increased diversity. But for sure, you need to synchronize this with this generation time for speciation.
So your model, I wanted to ask this also from Marcus. So they're like two to the B parameters, two to the B possibilities, right? But you only have a few colors. So wouldn't it be more accurate to have a continuous spectrum, and maybe where you have speciation and the continuous spectrum breaks, instead of trying to model it with just 5 or 6 colors?
So,
do you understand my question?
yeah, but
So
maybe,
example,
yeah, I'm trying so maybe the answer would be here, how we define a species.
So for example, in the ring species that,
Yeah,
that
so
Marcus
species is not how many different types we have. So to be species, they do not to be equal. They do not be clonal. They just need to allow gene flow. So they need to have a minimal similarity.
I understand, but there's a continuum. That's what, I mean, almost a continuum. There's 2 to the B possibilities.
To possibility for
2
the
to the
genome
B.
configuration.
Right. So
And if it is 2 to the power B genome of configuration, so it's proportional to that, the number of species. And that's true. Oh,
I
please.
guess I'm asking in the ring, for example, in the ring species.
There are many people asking for questions, and we do not have time. Maybe just one from who wants to? A student, yes.
Hi, it's really amazing, really cool. I was thinking that this definition of phylogenetic tree that you have, it's based on this emergence and disappearing of species, right? But in the sense that we have more standardized nowadays, that the genetics established is just sampling one individual and basing the phylogenetic with its own DNA. So how these two relate to each other?
Oh, it's something that I would like to do. It's a project that there is a student trying to look at this. So we can impose this mating restriction, but as people usually define the phylogeny, it's how similar one group is to the other. So we have clusters. So maybe here, what we call one species, maybe for empirical data would be 2, 3 species, because maybe we have cluster here already in this. It's not a unique cluster. So they start to divide. So we didn't look at that. We need to I think we should look more careful on that. It's a good thing. Thank you. Good question.
I'm so sorry, everyone, but in the interest of time, let's thank Sabrina again.
Thank you.